Welcome friends. In this session we discuss linear programming problem. Programming is just another word for planning and refers to the process of determining a particular plan of action from amongst several alternatives. That is the process of determining optimal allocations of limited resource to meet the given objective. There are many practical situations which involves the solutions of making the optimal use of limited resources so as to maximize profit or to maximize production or to minimize cost, etc. Such problems are the problems of constraint optimization. The solution of the problem is to select the optimal decision amongst the various possibilities. Hence, they are programming problems. Linear programming refers to the technique of finding an optimal solution to a problem with limited resources, where all the relationship between the variables under consideration are linear. Mathematical formulation of the problem. Various methods of solving linear programming problem involves graphical method, simplest method, etc. To apply the above methods to solve a programming problem, the first step is to identify whether the programming problem considered is linear or not. For this, it is to formulate the problem mathematically. The objective of the problem and the limitations in the resources are to be mathematically expressed using variables. The mathematical form of the objective of the problem is termed as the objective function, and that of the limitations in the resources are called constraints. In the mathematical formulation of the problem, if the objective function and all the constraints are linear functions of the variables, then the given problem is a linear programming problem. Mathematical formulation of the linear programming problem involves the following steps. 1. Write down the decision variables of the problem. 2. Formulate the objective function to be optimized as a linear function of the decision variables. 3. Formulate the other conditions or limitations in resources of the problem in terms of the decision variables. 4. Add non-negativity constraint from the consideration that negative values of the decision variables do not have any valid physical interpretation. Consider the following problems illustrating mathematical formulation of linear programming problems. First problem is a production allocation problem. A manufacturer produces two types of models A and B. Each A model requires 4 hours of grinding and 2 hours of polishing, whereas each B model requires 2 hours of grinding and 5 hours of polishing. The manufacturer has 2 grinders and 3 polishers. Each grinder works for 40 hours a week and each polisher works for 60 hours a week. Profit on model A is rupees 3 and on model B is rupees 4. Whatever is produced in a week is sold in the market. How should the manufacturer allocate his production capacity to the two types of models so that he may make the maximum profit in a week? In this question, it is a profit maximization problem. So, many restrictions are also here. So, in the mathematical formulation, the objective of the problem is to identify the optimal number of the two models to be produced so as to maximize the profit of the manufacturer. Let x1 and x2 respectively be the decision variables denoting the number of A model and B model to be produced weekly to maximize the profit. A model, let it be x1, and B model, let it be x2. So, his weekly profit, that means the profit on the model A is 3 rupees and profit through model B is 4 rupees. So, the total profit that he can earn by selling these products x1 quantity of A and x2 quantity of B, that is 3 x1 plus 4 x2. Let it be Z equal to 3 x1 plus 4 x2. Now, the problem comes to maximize the value of Z. That is, the objective function of the problem is Z equal to the maximize Z equal to, objective of the problem is to maximize Z equal to 3 x1 plus 4 x2. But the total number of grinding hours needed per week for model A is 4 and for model B is 2. So, if x1 quantity of A is produced, the total grinding hour requires for that number of capital x1 items of capital B, capital A is, or A model is 4 x1, and the grinding hour required for B model is 2 hours. So, for x2 items of B model, the total grinding hour required is 2 x2. So, the total grinding hour requires for producing x1 of A model and x2 of B model is 4 x1 plus 2 x2. But the total available grinding hour is limited. In the same way, the total number of polishing hours needed per week for model A is 2 and total number of polishing hour required for model B, that is 5. Hence, if x1 quantity of A and x2 quantity of B are produced, the total polishing hour required for these two items, quantity of these two items, that is 2 x1 plus 5 x2. This is the total polishing hour required for x1 of model A, x2 of model B. Hence, the total number of polishing hour is also mentioned. Since the maximum working time of a grinder is 40 hours per week, the maximum working time of 2 grinders is 80 hours per week. Therefore, 4 x1 plus 2 x2 cannot exceed 80. Here 2 grinders are here. So, this 4 x1 plus 2 x2 should be less than or equal to 80. That is one of the restriction. Then similarly, the maximum working time of 3 polishers are available. For one polisher, the maximum available time is 60 hours. So, for 3 polishers, 3 into 60, that is 180 hours per week available. But for producing x1 of item A and x2 of item B, total required polishing hour is 2 x1 plus 5 x2. Total available is 180. So, this cannot exceed 180. So, it should be less than or equal to 180. That is the second restriction, 2 x1 plus 5 x2 less than or equal to 180. Also, since it is not possible to produce a negative number of models, it is obvious that we must also have x1, definitely x1 greater than or equal to 0 and x2 greater than or equal to 0. Hence, the manufacturer's allocation problem can be formulated. The total problem is formulated mathematically as maximize Z equal to, that is his profit, 3 x1 plus 4 x2, subject to the conditions or restrictions, that is 4 x1 plus 2 x2 less than or equal to 80, and second restriction, that is 2 x1 plus 5 x2 less than or equal to 180, and x1 greater than or equal to 0, x2 greater than or equal to 0. Under this criterion, he can find out the best values of x1 and x2 so as to maximize the value of Z. That is a mathematical formulation of the problem. In another problem, we can consider the problem is a firm can produce 3 types of clothes, say A, B and C. 3 kind of wool are required for it, say red wool, green wool, red, green and blue wool. 1 unit length of type A cloth needs 2 meter of red wool and 3 meter of blue wool. 1 unit of type clothes are type A, B and C. for this the cloths required 2 meter of 2 meter of red wool, 2 meter of red wool and 3 meters of blue, 3 meters of blue. 1 unit length of type B cloth needs 3 meters of red, 3 meters of red wool and 2 meters of green wool, 2 meters of green, and in addition it required 2 meters of blue wool also. But the cloth C needs 5 meters of green, 5 meters of green and 4 meters of blue, 4 meters of blue. The firm has only a stock of 8 meters of red wool, 8 meters of red wool, 10 meters of green wool and 15 meters of blue wool. It is assumed that the income obtained from 1 unit length of type A cloth is 30. Income from A, 1 unit length of cloth A, the income is 30, and income from 1 unit length of cloth B, that is 50, and from that of cloth C it is 40. So, it is to formulate the above as a linear programming problem to determine how the firm should use the available material so as to maximize the total income from the finished cloth. So, definitely the objective is to maximize the profit of the maximize the income by making different length of or different types of cloths. So, we are assuming let x1 denote the total length of A cloth produced and total units of A cloth produced, and x2 that of B and x3 that of C, total unit length. So, the profit obtained or income obtained from x1, that is unit length of A cloth is 30. So, if x1 unit is produced, then total profit is 30 x1 plus x2 units of B produced profit, that is 50 x1 plus x3 unit of C produced, so profit is 40 x3. So, Z equal to consider Z equal to 30 x1 plus 50 x2 plus 40 x3. That is the total income that can be obtained by producing these 3 cloths of x1 and x1, x2 and x3 unit lengths. But to producing these cloths, there are many restrictions because the availability of various cloths are limited. So, considering all these restrictions, it is to find out the values of x1, x2 and x3 so as to maximize the value of Z. The restrictions are 1 unit length of type A cloth needs 3 meters of blue wool, B cloth needs 2 meters of blue wool and C cloth needs 4 meters of blue wool, but the stock of blue wool is only 15 meters. So, the maximum usage of blue wool should be 15, that is 3 into x1 plus 2 into x2 plus 4 into x3 should be less than or equal to 15. In the same way, 1 unit length of type B cloth needs 2 meters of green wool and C cloth needs 5 meters of green wool, but the stock of green wool is only 10 meters. So, the maximum usage of green wool should be 10. Hence, 2 into x2 plus 5 into x3, that should be less than or equal to 10. Since it is not possible to produce a negative number of cloths, it is obvious that we must also have x 1 greater than or equal to 0, x 2 greater than or equal to 0 and x 3 greater than or equal to 0. Hence, the problem can be formulated mathematically as find three real numbers x 1, x 2 and x 3, so as to maximize 30 x 1 plus 50 x 2 plus 40 x 3 subject to the restrictions 2 x 1 plus 3 x 2 less than or equal to 8, 3 x 1 plus 2 x 2 plus 4 x 3 less than or equal to 15 and 2 x 2 plus 5 x 3 less than or equal to 10, under the condition x 1 greater than or equal to 0, x 2 greater than or equal to 0 and x 3 greater than or equal to 0. That is the mathematical formulation of the given problem. You can write as maximize z equal to this much under these conditions. Now, we can consider another situation. Consider a factory with three types of machines A, B and C, which can turn out for four products 1, 2, 3 and 4 products 1, 2, 3 and 4. Any one of the product has to undergo some operation on each of the three types of machines. We shall assume that the production is continuous and that each product must first go on machine type A, then B, finally C. Furthermore, we shall assume that the time required for adjusting the setup of each machine to a different operation when production shift from one product to another is negligible. The table shows the hours required on each machine type per unit of each product, the total available machine hours per week and the profit realized on the sale of 1 unit of any one of the products. We want to mathematically formulate the problem. It is given like this: machine type, then products and total time. Here the products are 4 different products are 1, 2, 3 and 4. 4 different products are here. Then total time available total time per week, available total time per week. So, the types of machines, they are A, B and C. Then for the products for the product A, it is 1.5 hours required, then for product 2 1 hour, then for 3 2.4 and then for the last 1 hour. But the total available time of the machine A per week, that is limited to 2000. Then next for the machine B, the time required for the first product 1 hour, for the second product 5 hour, then 1 hour, then 3.5 hour. Total available time for the machine B, that is 8000 hours. And for the machine C, it is given as 1.5, 3, 3.5 and 1. Total available time is 5000. Unit of the profit from each product. From the product 1 unit of product 1 gives the profit of 5.24 and 1 unit of type product 2 gives profit of 7.3, then this gives profit of 8.34 and the last one gives the profit of 4.18. So, we want to mathematically formulate this problem, what quantities of the products 1, 2, 3 and 4 are to be produced so as to maximize the profit. For this, we are assuming x1, x2, x3 and x4 are the units of the products 1, 2, 3 and 4 produced. If x1, x2, x3 and x4 quantities of these products are produced, then the total profit earned is 5.24 into x1 plus 7.3 into x2 plus 8.34 into x3 plus 4.18 into x4. Let this be said. So, now our problem is to maximize the profit, that is z equal to 5.24 x1 plus 7.32 x3x plus 8.34 x3 plus 4.18 x4. But the limitation is the available time of these three types of machines. These three types of machines are required to complete these products. Their total available time per week is limited. That is the restriction of finding out the values of x1, x2, x3 and x4 so as to maximize Z. Then we want to formulate the restrictions also. So, the total available time of the machine A per week is 2000. For product 1, 1.5 hours of machine A is required. For product 2, 1 hour, product 3, 2.4 and product 4, 1 hour of time, 1 hour time of machine A is required. So, if x1, x2, x3, x4 items of products 1, 2, 3 and 4 are produced, the total required time of machine A is 1.5 x1 plus 1 x2 plus 2.4 x3 plus 1 x4. But the total available time of machine is limited to 20,000. So, this value should be less than or equal 2000. So, this should be less than or equal to 2000. Now, when we are going to the machine B, the total available time of the machine B per week is 8,000. So, if the items x1, x2 and x3 and x4 quantities are produced, the total hour of the machine B required is 1 x1 plus 5 x2 plus 1 x3 plus 3.5 x4. This should not exceed 8,000, that means less than or equal to 8,000. In the same way, when we are considering the machine C, the total available time is 5,000. So, the total available time of total required time of the machine C should not be greater than 5,000, that should be less than or equal to 5,000. The time required by the machine C to produce x1, x2, x3 and x4 quantities of the products, that is 1.5 into x1 plus 3 into x2 plus 3.5 into x3 plus 1 into x4. This should be less than or equal to 5,000. So, these are the three restrictions with respect to the available time of the machines A, B and C. And again, the units produced is x1, x2 and x3, they cannot be negative. So, x1, x2, x3 and x4 are the number of units produced, number of units of products produced. So, they all should be greater than or equal to 0. So, keeping all these restrictions, we want to identify the best values of x1 and x2, x3 and x4 so as to maximize the value of Z. That is, our problem is reduced as a linear programming problem so as to maximize Z equal to 5.24 x1 plus 7.3 x2 plus 8.34 x3 plus 4.18 x4 subject to these three criteria restrictions and non-negativity conditions x1, x2, x3, x4 greater than or equal to 0. Now, we are moving to familiarize with the method of solving the linear programming problem. The first method that we are going to discuss is graphical method of solving LPP, linear programming problem. Graphical method. So, if the linear programming problem contains only two variables, it can be solved graphically. The steps required for solving a linear programming problem using graph are: 1. Formulate the given problem into a linear programming problem as we already considered. each constraint inequality may be considered as equality. 3. Draw straight lines corresponding to the constraints which are considered as equalities. There will be many straight lines as there are many constraints. 4. Identify the region which satisfies all the constraints simultaneously. 5. The region identified in a many-sided figure, the corner points of the region are to be located and their coordinates x1, x2 are to be noted. Calculate the value of the objective function z corresponds to each corner point x1, x2. The solution of the linear programming problem is given by the coordinates of that corner point x1, x2 which optimize the objective function. We can consider some problem to illustrate the procedure of graphical methods. The first one, solve the following linear programming problem graphically. The problem is maximize z equal to 6x1 plus 11x2. This is the objective function to maximize 6x1 plus 11x2. There are some constraints, they are 2x1 plus x2 less than or equal to 104, first constraint. Next constraint is x1 plus 2x2 less than or equal to 76 and x1 greater than or equal to 0, x2 greater than or equal to 0. So, we want to identify the best values of x1 and x2 or the most suitable values of x1 and x2. So, as to maximize the value of z keeping all these restrictions. So, here by step 1 the problem readily given in the LPP form. So, nothing to be done more. Then step 2 write the inequality to equality form. So, here first of all 2x1 plus x2 I am writing it is equal to 104 and the next is x1 plus 2x2 as equal to 76. So, in a graph paper I want to draw these two lines. One is 2x1 plus x2 equal to 104 and x1 plus 2x2 equal to 76. So, to draw 2x1 plus x2 equal to 104, I am first of all I am considering x2 equal to 0. When x2 equal to 0, I am getting 2x1 equal to 104. So, x1 equal to 52. So, first point is 52, 0 for the line, for drawing the line 2x1 plus x2 equal to 104. And next I am substituting x2 equal to 0, sorry x1 equal to 0. When x1 equal to 0, I am getting x2 equal to 104. That is the point is 0, 104. So, we can note these 2 points 52, 0 and 0, 104 on this graph. So, x value is 52, let it be 10, 20, 30, 40, 50, now somewhere here it is 52, 52, 0 and another point is 0, 104, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, somewhere here you can get this point 104, 0, 0, 104 and here it is 52, 0. Joining these 2 points, this is the graph of or this straight line 2x1 plus x2 equal to 104. In the restriction it is given 2x1 plus x2 should be less than or equal to 104. So, on this line 2x1 plus x2 equal to 104, one side of this line 2x1 plus x2 greater than 104 and on another side 2x1 plus x2 less than 104. We can consider these points 0, 0. When x1 is 0 and x2 is 0, 2 into 0 plus 0 that is 0, that is less than 104. So, on this side 2x1 plus x2 less than 104. So, all the points of this side are our required points. Then the next is x1 plus 2x2 equal to 76, that is the next straight line. So, again we want to draw that straight line x1 plus 2x2 equal to 76. For that, assume x1 equal to 0. When x1 equal to 0, 2x2 equal to 76 or x2 equal to 38. So, the point is 0, 38. Next, when we are assuming x2 equal to 0, we are getting x1 equal to 76. So, the point is 76, 0. So, on this graph we are plotting these 2 points 76, 0 and 0, 38. 76, 0, 50, 60, 70, somewhere here 76, 0. And next is 0, 38, 0, 10, 20, 30, 38, somewhere here 0, 38. So, joining these 2 points 0, 38 and 76, 0, we are getting a straight line x1 plus 2x2 equal to 76. Again, in this restriction x1 plus 2x2 should be less than or equal to 76. So, on this straight line x1 plus x2 equal to 76, one side of this straight line x1 plus x2 less than 76 and on another side x1 plus x2 is greater than 76. Assume for the point 0, 0, when x1 0, x2 0, we are getting this side 0 which is less than 76. So, on this side of this line x1 plus x2 less than 76, we are shading. And then next condition, x1 should be greater than or equal to 0. The value of x1 should be greater than or equal to 0 and x2 also should be greater than or equal to 0. So, here we can see the region where all the shades are intersecting, that is this region. In this region all the restrictions are satisfied, points of this region are satisfying all the restrictions. So, the possible values of x1 and x2 are lying in this region, but there is a theorem. According to that theorem, we are just checking the corner points of this region. So, 4 corner points are 1, 2, 3 and 4, 4 corner points are here. So, the values of x1 and x2, that is on the coordinates of these 3 corner points will give us the best values of x1 and x2. For that, the first corner point, it is here we know 0, 0 and this corner point, that is 52, 0, and to get the third, let it be first is A, second is B and third one is C and fourth one is D. The only unknown corner point is C. To get that corner point, we want to solve these 2 lines, because these 2 lines are intersecting at the point C. They are x1 plus 2x2 equal to 76 and 2x1 plus x2 equal to 104. So, multiplying the first one by 2, so we are getting 2 into x1 plus 4 into x2 equal to 76 into 2, 152. Let it be 3, this is 1, this is 2 and 3. Subtracting 2 from 3, but we are getting 2x1 minus 3 minus 2x1 minus 2x1 0, 4x2 minus x2, that is 3x2 equal to 152 minus 104, that is 48. 3x2 equal to 48, that means x2 equal to 48 divided by 3, that is equal to 16. We are getting the value of x2 as 16. Substituting this value of x2 16 in any one of the equation, let it be in equation number 1, we are getting x1 plus 2 into 16 equal to 76, that is x1 plus 32 equal to 76. This gives x1 equal to 76 minus 32, that is equal to 44. So, the coordinates of the vertex C, that is x coordinate is x1, that is 44 and y coordinate is 16, 44, 16. Now, we want to check the best value of x1 and x2, and by a theorem it is given the best values of x1 and x2 will lie on any of the vertex of this area, that is this area is the area common for all the constraints. So, we want to identify the values of z on all these vertices. At A, that is 0, 0, the value of z is equal to 0, Then next at B, we are giving the value name for this vertex A, B, C and D. So, at B 52, 0, the value of Z is equal to 6 into 52 plus 11 into 0, that is equal to 312. Then at C 44, 16, the value of Z is equal to 6 into 44 plus 11 into 16, that is equal to 6 into 44. 264 plus 11 into 16, 176. So, total is 440. And finally, at D, the D is 0, 38. The value of Z is 6 into 0 plus 11 into 38, that is 38. So, we are getting it as 418. So, when we are considering the values of Z at these 4 different vertices, we are getting at C the value of Z is maximum, that is it is 440. For the values of x1 is equal to 44 and x2 equal to 16. Hence, the solution of this linear programming problem by this graphical method is the maximum value of Z is 440, that can be attained is 440 when the value of x1 is equal to 44 and x2 equal to 16. So, this is the solution for the given linear programming problem by the method of graph. We can consider another problem. So, in the next problem, it is to solve the LPP, maximize 5x1 plus 3x2, maximize Z equal to 5x1 plus 3x2. The constraints are 4x1 plus 5x2 less than or equal to 10, then 5x1 plus 2x2, 5x1 plus 2x2 less than or equal to 10, and 3x1 plus 8x2, 3x1 plus 8x2 less than or equal to 12, and finally x1 x2 greater than or equal to 0. So, in this problem there are only 2 variables x1 and x2. So, we can solve the problem graphically. So, to solve the problem graphically, we are drawing the constraint equations. They are 4x1 plus 5x2 equal to 10, 5x1 plus 2x2 equal to 10, 3x1 plus 8x2 equal to 12. To draw this straight line, 4x1 plus 5x2 equal to 10, let x1 equal to 0. This implies x2 equal to 10 divided by 5, that is 2, and x2 equal to 0 implies x1 equal to 10 divided by 4, that is 2.5. So, the points are 0, 2 and 2.5, 0. So, let it be 1, 2, 3, 4, 5, 6, 7. Similarly, 1, 2, 3, 4, 5, 6, 7. So, the point is 0, 2, x value 0, y value 2, this one point. Then x value 2.5, y value 0, 2.50, 0, 2. So, joining these 2 points, we are getting the straight line 4x1 plus 5x2 equal to 10. In the constraint 4x1 plus 5x2 less than or equal to 10. So, in this side of the straight line, the shaded part of the straight line, 4x1 plus 5x2 less than 10. So, this region including this straight line 4x1 plus 5x2 less than or equal to 10. Next is 5x1 plus 2x2 equal to 10. To draw the straight line 5x1 plus 2x2 equal to 10, let x1 equal to 0, then x2 equal to 10 divided by 2x2 will be 10, or x2 equal to 10 divided by 2, that is 5. So, first point is 0, 5. Next assume x2 0, when x2 0, 5 x1 equal to 10, or x1 equal to 10 divided by 5, that is 2. When x2 0, x1 equal to 10 divided by 5, that is 2. So, the next point is 2 0, x1 2, x2 0. So, the point 0 5, 0 1 2 3 4 5, 0 5 is one point and another point is 2 0. Joining these 2 points, we are getting another straight line, that is 5 x1 plus 2 x2 equal to 10. Next, to draw 3 x1 plus 8 x2 equal to 12. For that, x1 equal to 0 implies 8 x2 equal to 12, or x2 equal to 12 divided by 8. Then that is equal to 1.5. And when x2 equal to 0, x1 equal to 12 divided by 3, that is equal to 4. So, the points are x1 0, x2 1.5, 0 1.5, and the next point is x1 4, x2 0, 0 1.5 4 0, 0 1.5, that is here 0 1.5, and next is 1 2 3 4, 4 0. Joining these 2 points, we are getting another straight line, that is 3 x1 plus 8 x2 equal to 12. So, in all these constraints, the 5 x1 plus 2 x2 less than or equal to 10, 3 x1 plus 8 x2 less than or equal to 12. So, graphs are, or shaded region are like this. And x1 x2 greater than or equal to 0, x1 greater than or equal to 0, x1 greater than or equal to 0, x2 greater than or equal to 0, x1 x2 greater than or equal to 0. So, here we are getting a region where all the shades are intersecting. In this region all the shades are intersecting. So, this is the solution region. So, in this solution region the best values of x1 and x2 are lying, but it is given one of the vertex of this solution region will give us the best values of x1 and x2. So, to identify what are the vertices of this solution region, first one is, let it be A, B, C, D and E. So, A is 0 0, B is 2 0, C and D are to be identified, E is 0 1.5. These are the 5 vertices of this solution region. Now, to identify the values of vertices of C and D, we want to solve the corresponding equations. First one, to get the value of C, we want to solve the straight lines 5 x1 plus 2 x2 equal to 10 and 4 x1 plus 5 x2 equal to 10, because C is the point of intersection of these two straight lines 5 x1 plus 2 x2 equal to 10 and 4 x1 plus 5 x2 equal to 10. So, let us multiply the first let it be equation number 1 and equation number 2. Let it be multiplied by 5. So, 25 x1 plus 10 x2 equal to 53. Let the second is multiplied by 2. So, 8 x1 plus 10 x2 equal to 20. Let it be 4. 3 minus 4 implies 28 x 1 minus 8 x 1, that is 17 x 1 equal to 50 minus 30, that is 50 minus 20, that is equal to 30, or x 1 equal to 30 divided by 17, x 1 equal to 30 divided by 17. Now, substitute in some of the equation the value of x 1 we are getting. So, substitute it in equation number 1. So, 5 into 30 divided by 17 plus 2 into x 2 equal to 10, that is 150 divided by 17 plus 2 x 2 equal to 10, or 2 x 2 equal to 10 minus 150 divided by 17, or 170 minus 150 divided by 17, that is equal to 20 divided by 17. So, x 2 equal to 20 divided by 17 divided by 2, that is 10 divided by 17. So, we are getting the C as 30 divided by 17 comma 10 divided by 17, that is the coordinate of the point C, 30 divided by 17 comma 10 divided by 17. Similarly, you want to identify the value of the coordinate D also. To get D, it is to solve the two straight lines, they are 4 x 1 plus 5 x 2, 4 x 1 plus 5 x 2 equal to 10, and 3 x 1 plus 8 x 2 equal to 12. Multiply the first by 3, that is 12 x 1 plus 15 x 2 equal to 30, that will be 3. Multiply the second one by 4, that is 12 x 1 plus 32 x 2 equal to 48, that will be 4. 4 minus 3 implies 32 x 2 minus 15 x 2, that is 17 x 2 equal to 48 minus 30, that is 18, or x 2 equal to 18 divided by 17, and substituting in one of the equation, that is 4 into x 1 plus 5 into 18 divided by 17 equal to 10. This gives 4 into x 1 plus 5 into 18, that is 90 divided by 17 equal to 10, or 4 x 1 is equal to 10 minus 90 divided by 17, okay. That is 170 minus 90, that is 80 divided by 17, or this implies x 1 is equal to 80 divided by 17 into 4, 4 and 80 can be cancelled, that is 20 divided by 17. So, the D coordinate that we are getting, x 1 value is 20 divided by 17 and x 2 value is 18 divided by 17. Okay. So, we got the 5 coordinates of the solution vertices of the solution region as 0 0, 2 0, 30 by 17, 10 by 17, D 20 by 17, 18 by 17, and E 0, 1.5. Now, our job is to identify the values of Z for these 5 different vertices. At A, the value of Z definitely it is 0. At B, the value of Z is 5 into the value of x 1 is 2, 5 into 2 plus 3 into 0, that is 10, 5 into 2. Next, at C, the value of Z is 5 into 30 divided by 17 plus 3 into 10 divided by 17, that is equal to 150 divided by 17 plus 30 divided by 17, that is 180 divided by 17. Next, at D, the value of Z is equal to 5 into 20 by 17 plus 3 into 18 by 17, that is equal to 100 by 17 plus 54 divided by 17, that is equal to 154 divided by 17. And finally, at E, the value of z is equal to 5 into 0 plus 3 into 1.5, that is 4.5. So, these are the different values of z at the different vertices of the solution region. Among these, we can identify where the value of z becomes maximum. At C the value of z, that is 180 divided by 17, that is the maximum value of z. So, the solution of this problem is the maximum value of z is 180 divided by 17 at the points x1 is at the value x1 is equal to 30 divided by 17 and x2 equal to 10 divided by 17. So, all linear programming problems may not have an optimal solution. If the linear programming problem is having no solution, we are not attaining a solution region satisfying all the constraints. For some problems, the value of the decision variables is permitted to increase infinitely without violating the constraints. Then the solution is said to be unbounded. Here, the objective function value is also increased indefinitely. In such cases, there is an unbounded region as a solution region. Unfortunately, the graphical method cannot be used with more than 2 or possibly 3 variables. Then it is to rely on the algebraic method of solving linear programming problem known as simplex method. So, now we are concluding our session here. Thank you for watching this video. Hope you enjoyed this. See you next time. Goodbye.